Okay, in this video we're going to learn about Rolle's theorem and the mean value theorem. Rolle's theorem simply says that if f is some function and it is continuous on a closed interval from a to b, and it's also differentiable on the open interval a to b, meaning that within this continuous part of a to b there are no places where the tangent goes vertical, and there's no like little V shapes or cusps. And the third condition of Rolle's theorem is that the endpoints f of a and f of b are equal. So if those three conditions are met, it says that there is some number c in this interval from a to b such that the derivative at the value c is equal to 0, meaning that it's you can find a horizontal tangent somewhere in that interval. So it doesn't tell us where to find it, but it does say that it exists. So let's just imagine some different scenarios of functions that meet this condition. We could draw some different functions just to get an idea of what Rolle's theorem is saying. So let's just say here is a and here is b on each of these. Some closed interval a to b, and it's got to be continuous and differentiable. That's the only two conditions. You could have something, you could have an endpoint here a, and then you could have it go up, and then at b it could be at the same place it was at a. We could have it like here. That's a pretty bad drawing. Let me try that again, because it looks like it goes vertical. I didn't mean to make it go vertical. But basically, the third condition is that the output, the y value of a and the y value of b have to be equal. So let me just start here. So let's say a goes up and it does some crazy stuff, and then it lands down here at b. Okay, it could do that. Maybe you have a case where here's a and the output of b has to be the same, and in between you just have to make it continuous. You could make it straight if you wanted to. You could say a could be, you could start here at a and b has to be the same. That's the third condition. How do you want to connect these two? You could make it so that it went up if you wanted to. If here, we could make a and b, they just have to be the same, starting in the same. You could make it wavy in between, or you could make it sloped. We could do one little jog in between. It's just whatever somehow we have to connect those in a way that it's continuous and it doesn't make a big vertical tangent line or cusp. So what is the conditions? If all three of those are met, and they are in each of these cases, then there's some number c such that the derivative of c is equal to 0. Where would the derivative of c, or the slope of the tangent line, be 0? At these it's horizontal. That's wherever it's a horizontal tangent. So right there, right there, right there. So we see in this first scenario, the Rolle's theorem is satisfied in 3 places. So you could call this what you call the C1, C2, C3. There's 3 places. Where is it satisfied in this second graph? It's satisfied in infinite many places, because at every place along this function it's got a horizontal tangent in that case. So definitely at least one. Between a and b here, just once, I think, just right here. This would be the value of c where it's satisfied. What about here between a and b? Here's one place and here's another place. So that would have 2, C1 and C2, 2 values that would be satisfied. After that, we can consider this other theorem, the mean value theorem. The mean value theorem is similar to Rolle's theorem. It says let f be a function that satisfies the following hypotheses. And so the first one is the same. F is continuous on a closed interval from a to b. F is differentiable on an open interval from a to b. And it doesn't say that f of a has to equal b, so that's different, but it says this. Then there is some number c on this open interval such that the derivative at that point c is equal to the slope, if you look at this, of the secant line, where the secant line is formed between the endpoints a and b. y2 minus y1 over x2 minus x1, basically. Well, here's the endpoints. A, f of a